Hello, this is Dr. Kraus with what I intend to be the final part of my Bode series, unless I'm really hit with inspiration after this. This is an experimental kind of culmination, bringing together what we've done, and just want to talk about mainly this beam. It's a 3D printed plastic beam attached to a DC motor that has a gear head with an encoder on the back of the motor and then an accelerometer measuring the tip acceleration. This is a 6AA battery pack. There's an H-bridge shield on top of my Arduino Uno knockoff. And then this is a custom PCB that just makes the connections between the motor and the encoder and the appropriate pins on the Arduino. So let's start with a couple of block diagrams. I'd like to show you both the open loop and closed loop so that you understand some of my variable names and kind of the terms that I'm using and that sort of thing. So in open loop, I have a voltage, which is really a PWM, although it can also possibly be signed, um, and that's going to get handled by the H-bridge. And so that's going to ultimately go to the H-bridge and the motor. And when it moves that motion, I'm going to call that theta. That's going to be measured by the encoder itself on the back end of the motor. And then the theta motion will also cause the beam to move because it's attached, um, possibly also, probably also causing vibration at the tip that will be measured with my accelerometer. Then when we get to closed loop testing, we are going to have some desired closed loop input. I'm going to call that U out of habit, but you could also think of that as the desired theta. We'll send that in and compare it to a measured theta that will lead to an error signal that will feed into the controller transfer function, which will probably be PD control in this instance. So that will lead to our V, which again is a sort of a PWM, but with a sign that gets handled by the H-bridge having some enable pins that determine direction. Ultimately, we take the ABS of that absolute value of that voltage, and that's actually the PWM after the direction pins are handled. So that goes out to the motor, and the motor would then cause rotation that gets measured with our encoder, and then that goes to the beam because the beam again is attached, and so that ultimately produces tip acceleration measured again with our accelerometer. So the difference being in closed loop control, we measure theta and feed it back and use this error to determine the input to the motor. Part of the reason why this is necessary, when it comes to swept sign experiments, you cannot do swept sign on an unstable system. It just won't lead to physically meaningful results and may potentially break things. But in our case, we've got a pure integrator in our plant, which I know from experience, and swept sign tests work best when you can start and stop at the same point and not have them drift off, and pure integrators can often do that experimentally. So we're going to use feedback control on the swept sign to prevent that kind of drift. Okay, so I think we're ready to run some experiments. If you've watched any of my previous videos or are one of my students, it won't surprise you that I've got some custom Python code that's going to connect to the Arduino over serial to command the Arduino to run some different experiments, and then also to capture and plot the data. So I've established a serial connection with my Arduino. I'm going to quickly do an inverse deadband calibration to find out what PWM values are necessary to cause positive and negative motion. And then I'm ready to run an open loop pulse test. I'm going to hit enter and have 2 seconds to flip over here and show you the actual experiment. So it's just, well, let's look at the data. There is an open loop pulse voltage that goes to the motors, and then that causes some amount of theta motion and some amount of tip vibration. So one, you could probably start to talk about what's the natural frequency of that beam by just looking at, and even the damping if you really wanted to get wild and crazy, with fitting that X double dot decay, sort of an impulse response. Another thing to note is that we've given a finite width pulse that comes back to 0, but theta does not come back to 0. So that's one of the telltale signs of a pure integrator in our plant. But if we were trying to find some of the transfer functions that I had shown in the block diagram previously, that may or may not, I mean, that this is better than nothing. This is some kind of data. Maybe you could fit it, maybe you can't. My argument is that we're going to run a few more experiments and kind of see what we can learn. So I'm going to reset that to something that's inside the camera. I could then switch over to a closed loop, and I could run a step response. Again, I'm going to give myself 2 seconds to enter the command and flip over to here so that you can see that it actually runs a physical experiment. It moves, and then there's a little bit of vibration at the end. And so if I plot that, this is theta, and because of my choice of Kp and Kd, my theta is actually slightly underdamped. And then I've got this now aqua colored line that is the vibration of my tip. So the time domain test results are useful and could be used in a number of ways to try to squeeze out information about the transfer functions. But since this is a series of videos on frequency response, it shouldn't surprise you that I'm going to argue that frequency response can potentially get you more information, and just want to show an example of how it's done. So there's a couple of different ways to go about that. One is to do a fixed sign input. So you would just pick particular frequencies. The slightly tricky part is knowing what frequencies to pick. And so I'm going to just show you a couple of different examples. I'm going to call this a low frequency. This is a 1 hertz. And again, I'm going to start the test and then give myself 2 seconds. And it'll do its thing. And then we can look at that data. And that's a little, with all of the signals, that's a little bit hard to understand. So the main thing I want you to see at this point is that at low frequencies, the actual theta is able to fairly accurately track the desired input. Where the big battle there is kind of voltage versus friction. And then part of why that's important is if we actually looked at theta coming off the encoder versus the voltage into the H bridge, you can see here there's just a ton of high frequency jumping around, and basically that's the closed loop controller fighting against friction to get theta to track the desired theta. And so you kind of would have to pass filter that in your mind to see that there is a low frequency voltage that's also roughly 90 degrees ahead if I really wanted to read into that, because I know there's a pure integrator, I would expect that. And so theta lags V by about 90 degrees, but you would really have to want to see that. So if we were to then paste my little delay again, go up to, this is now 3 hertz, and so it's a higher frequency motion. The friction is a little bit less pronounced because we're at higher frequencies, but the thing to see now is that the desired closed loop theta is U. The actual theta is just called theta on this plot, and it's not tracking as well as clearly. And then if we look at the voltage versus theta, it's now taking a much larger PWM input to cause the motion that we're seeking. So we see less issues with noise because V is just larger. But if you look at that, it's fairly obvious that theta is now 180 degrees out of phase with V. And so we could do this again, and now I'm going to do it at 10 hertz. And so much higher frequency. Not sure if my camera is going to have some aliasing problems or not. But when I look at this data, one of the things we see is now the desired U is pretty high frequency as far as the system is concerned. And so theta doesn't really, there's like this low frequency kind of sliding around. It's just because essentially the U kind of becomes like a dither signal, and friction just kind of doesn't know how to respond to that. And so it tends to just kind of float around, but the actual amplitude at that 10 hertz frequency is not very large. And that's even more pronounced if we look at voltage versus or PWM signal versus theta. That's now a fairly large amplitude, and theta is just kind of, yeah, it's doing it a little bit, and then it's also drifting around a little bit, but there's just not nearly as much response. So one, if we've been thinking about Bode plots and frequency responses, we need to think in terms of the ratio of the amplitude of input to output, but also the phase relationship between input and output. Now, that's just me choosing 3 different frequencies for fixed sine testing and talking about their phase and magnitude relationships. But guessing exactly which frequencies are really important is a little bit complicated. So that's where the swept sine test comes in. We now want to basically let our, and I guess I can do this and just kind of show you up front, if I could spell. Just a little bit of lag here that's throwing me off. We're basically having U as a sine wave, but the frequency of the sine wave is itself a linear function of time. And so we start off at a fairly slow frequency sine wave, and then over time we get faster and faster and faster and faster. So we're going to take that input and send it to the system, and we'll see the response of this thing as the frequency changes over time. So let's do that now. And so it first moves slow, and then it moves faster and faster and faster. If you're watching really close, there's certain frequencies where the beam bends a lot, or mostly 1 at this point, because that's the first bending frequency of this beam. And so it kind of does its thing. And then we come over here and can look at that data. And so right in here is where the acceleration gets pretty large, and it's kind of hard to read the rest of it. So I saved data from a previous test. I guess I could save that one as well, and then wrote some code that just kind of analyzes that data. So we have this time domain test. Let's talk about how to get that into a Bode plot. So I'm going to leave it as the previous one that I did. I'm loading that data out of so it's a bunch of columns in a data file delimited by a tab or a comma or something. And so there's the data. If we look at it, we could also, might be slightly instructive to grab only a couple of those things and plot those. So let's look at the closed loop input desired theta versus the encoder. And so basically what you see is if we were to zoom in on the x-axis, it's able to track fairly well at low frequencies. I guess I could show you that zoomed in for a second. And then as the frequency starts to get higher and higher, the ability of the system to track the closed loop input gets worse and worse until we get up to a fairly high, and it's just kind of drifting around at low frequencies in response to friction and those kind of things, but it's not really tracking. So we want to do a Bode plot, but if we want that Bode plot to be meaningful, we have to have a frequency vector that goes along with it. Every Bode algorithm will return to you a complex vector of the real and imaginary part of doing the fast Fourier transform, but it does not give you the frequency vector to go along with it. So I'm going to create that frequency vector by first. So if you think about how you generate a time vector, you have a dt if you're making one up that just kind of steps along. Well, in the same way, we're going to have a df on our frequency vector, but that df turns out to be 1 over the total amount of time that we've acquired data for. And so if I take that df and multiply it by a vector that goes from 0 in steps of 1 as an integer to the number of data points in the file, then I can create a frequency vector, and that will stop at 1 df below our sampling frequency. So then if I want to start generating Bode plots to help me try to find transfer functions, I need to take the FFT of whatever output I want for my particular transfer function divided by the FFT of the input. So if we wanted to look at theta over the PWM signal, I could take FFT of the encoder divided by FFT of the voltage and call that my J omega 1. And then I can just plot that, find the dB magnitude and phase. And so there is the dB magnitude and phase of this particular set of data. And that might not look like a lot depending on your level of experience with these kind of things. But one of the things that always happens has to do with noise in the phase. And if I could try to explain this really quickly. If I had something that so I've got some GJ omega is a vector of complex numbers. If I have some real part and some imaginary part of that, if there was something that was supposed to be minus 180, so purely real in a negative sense, and if there was no noise in my data, I'd be right there. But what if, as I'm taking a bunch of data points, it's actually jumping around? The imaginary parts are supposed to be 0, but they're not quite 0 because of noise. Well, then when I take the arctan of that, I get some values that are like plus 179 degrees and some that are minus 179 degrees or whatever. Numbers around 180 that are just kind of jumping around. And then the same thing could happen if we had something that was supposed to be 0, but we sometimes get, now that's not quite as big a deal if it's plus or minus 1, but what if this batch of data is actually supposed to be minus 360 or that sort of thing. So it's always legitimate to add or subtract 360 degrees from your phase to make it better match up with what you expect out of your models. So what I see is a pure integrator in here that gets botched up by noise at low frequencies. So I expect my phase to be about minus 90. Because of friction, it's actually slightly below minus 90, which will maybe make you slightly uncomfortable. But then there's some kind of a glitch that goes up and down here. I think this is a 0 and a pole that are near each other, probably even a second order 0, a second order pole that are near each other. That caused that little glitch in the magnitude that also caused the phase to kind of jump around a little bit. But I think that most of in here, the phase is showing like it's positive 180 when really it should be minus 180. So my Bode utils code, which I talked about in a previous video, has a Bode plot 2 that takes a complex vector, but it returns the dB magnitude and phase. So I could now go to work on trying to clean up that phase. And so I'm just going to say wherever because I know it's got a pure integrator, I never expect the phase to be above 0. So I'm going to find out where in that entire vector are all the points that it's above negative 20, and then I'm just going to subtract 360 degrees. And so when I do that, I now have phase that's, again, slightly below minus 90. I appreciate that that kind of violates some rules that we established earlier on. This is not a purely linear system because of friction. But then I do see the phase go up for a little bit and then come back down. And so there is a pole 0 combination that are almost canceling each other's phase contributions. But because I kind of see a valley and a peak, I think it's a second order underdamped pole, second order underdamped 0. The 0 is actually lower frequency and they're kind of on top of each other. But if you wanted to prove that to yourself or do some kind of real stuff, then you could come in here and find a transfer function and overlay it and then try to curve fit to get the magnitude and or phase to agree with this experimental data. So that is the transfer function of the motor. We were talking about theta over V. If I wanted to talk about the beam, and again, you could just as legitimately plot the Bode plot of theta over U. That could be potentially useful. I also want to talk about accelerometer, and I'm going to use theta as the input, but you could also use V or U as a potential input. Just depends on how you want your data and your model to correspond. So if I wanted to try to generate the Bode plot of tip acceleration over encoder, I would take GG omega 2 is just the FFT of that accelerometer signal divided by the encoder signal. And again, I can immediately generate a Bode plot based on that, using Bode Plot 2 from my Bode utils function that expects a complex vector and then returns the dB magnitude and phase. Because there's an accelerometer involved, I expect my dB magnitude, so the accelerometer at low frequency should be 0, which on a dB magnitude should go to negative infinity. Because of noise, obviously, it's not going to go perfectly to 0, and so it's not perfect. But I see a pretty significant downward slope here, and then a peak, and then it kind of looks like it sort of levels off. So I would expect pure double differentiator, positive 180 degrees phase, and then a 180 degree phase drop. And so I'm going to assume that all of this is noise if the phase is below, I don't know, 30 or 40 or so. And so I'm going to do my phase. So I'm going to ask, where is the frequency below 4 hertz? 1, 2, 3, 4. That might not even be quite aggressive enough. And where is the phase below 0? And then I'm going to AND those two together. And in that frequency range with these phase issues, I'm going to add 360 degrees. And now my kind of massaged Bode plot looks like that. And I probably missed, this guy probably also needs 180 degrees added to him, although he's at minus 90, so that would send him up to plus 270. That's just probably noise, and there's probably nothing we're going to do to fix that. But again, I would claim, looking at this, that I see pure double integrator at low frequencies with 180 degree phase, a pretty fairly clear second order underdamped thing. This is noisy data. It's a low cost accelerometer. It might be not well suited in terms of its magnitude range. Don't know if I could do better. And also, whenever you're doing Bode testing, what you do as far as your input vector can have a huge effect on the quality of your data. And then you could also average these and do additional signal processing, whatever, whatever. But I'm going to claim that there's a natural frequency of this beam at the 1, 2, 3, right around 4 hertz range. So yeah, anytime I run an experiment where I've got reasonable frequency content on my input, I can find the Bode plot by taking the FFT of my output divided by the FFT of my input, and that will give me a complex vector that I can immediately find the dB magnitude and phase of. The kind of frustrating part is there's always going to be some massaging of the phase unless you get really, really lucky or your system is just really, really super linear. Um, Pretty unlikely. And so you got to kind of know what, like again, it's always legitimate to add or subtract 360 degrees. And then if that makes your Bode plot better agree with the model that you think explains the data, then I think you're on the right track. Thanks.